We have finished all the basic concepts of partial differential equations. We have now reached to a point where we are using the applications of partial differential equations. Again, a very interesting class of lecture that we will be having, class of concepts that we will be encountering with. We will be dealing with D'Alembert's solution of the wave equation, and later we will come to the heat equation in the next lecture. D'Alembert's solution is one of the best solutions that we have for one-dimensional and two-dimensional wave equation. As we proceed, we will be having almost all classes of this wave equations. One-dimensional wave equation and D'Alembert's solution. We'll have two things. Every differential equation has two main titles. One is a boundary value problem, another is an initial value problem. We'll define each of them. So let a differential equation corresponds to a particular physical problem, any physical problem that you are undertaking. When the differential equation is satisfied with certain reason, within certain reason means in a bounded reason, and certain conditions on the boundary means on the periphery of that, are also satisfied equally at the same time, then this problem is called boundary value problem, the first definition. Now, we come to one-dimensional wave equation. One-dimensional wave equation has this problem. We are imposing this problem because we would like to understand, in other words, that what we mean by one-dimensional wave equation and how it propagates, and we take therefore a problem to make it easier for us, for all of us to understand. An elastic string is stretched to length L, and ends of it are fixed to 2 points. One is 0, 0, the fixed point origin, and another to L0 on the x-axis, and therefore you can notice L is the abscissa of the second coordinate. The string is distorted, we give a vibration to it, and then released at t is equal to 0, that means the time when it starts, allowed to vibrate, keeps on vibrating. To find the deflection, deflection is given by this function. There is a function of x and t, t is a time, x is a variable of any point x at certain time which is positive and greater than 0. What we have these equations we must know. First we had the boundary value problem definition, then we had certain classification of it, and then we would like to understand the mechanical system, the vibration, the distortion, and then the release of the time at t is equal to 0. We assume the following before we come to actual solution of the problem undertaking. The string is homogeneous. Second is string is perfectly elastic. It does not offer any resistance or bending. Second is the tension caused in the string by stretching it before being fixed at the end point is very large in comparison to the force of gravity. Therefore, the effect of gravitational force is neglected. We don't take into account the gravitational force denoted by small g as the letter. And another assumption is each particle moves strictly vertically, which we call as transverse motion. Another is longitudinal motion. So, we have the transverse motion as such. The slope and deflection of any point at the string are very, very small. We avoid detailed mathematical calculation. What we conclude with is this equation. Plenty of calculations are involved in getting to equation 1, but what we intend to do is to give a very brief, and to remind you, we are still going on with the partial differential equation, same notation, d2u upon dt square, d2u dx square, which we have kept as r, and then d2u upon dt square. Everything is written, reduced slowly, and we arrive at the equation 1, which is in a very compact form, written as d2u dt square is equal to, this is c square d2u dx square, that is we mark as equation 1. In all these cases, we have rho as the mass per unit length of the string. Capital T is purely a constant. Partial derivatives are used because u is a function of two variables, u is dependent, and as you can see here, x and t are independent variables. Similarly, what we started when we started with the differential equation. The constant t upon rho is taken to be c square. Both are constant, so I can replace it with any other constant, c square, only to show that t upon rho is a positive quantity greater than 0. So, with all these notations, with all these assumptions, 3 assumptions if you note there, equation 1 will be called just now, is called one-dimensional wave equation. One-dimensional wave equation, that equation which we have studied. The solution becomes in the following line. We will have to follow these to get a solution of that equation number 1. We have the equation 1 as the vibration of a string, ends of which are tied to 2.00 and L0, both are coordinate systems. Moreover, this function u of xt, x is a variable, t is the time, is the deflection of the string, Let us assume that fx is the initial deflection and gx is the initial velocity of the string. Initial velocity and initial deflection are two different entities, but they play almost a similar role while we will be solving it. The function uxt will satisfy the equation 1 and the following boundary and initial conditions will be implied on them. The boundary conditions are given as this. Function of 0t is 0, function of Lt is 0, L is the length that defined earlier, that is the equation 2. We have the initial condition. Just now we were talking about two conditions, one is the boundary value problem, another is initial conditions, two conditions. Boundary conditions and initial conditions. We have talked about the boundary condition in the previous equation. Now we have the initial conditions given by 3 and 4. So, the function u of x and 0 is denoted by fx and partial derivative of with respect to t is given as gx. What our aim and objective is like this: we have to find a solution of the equation 1, which in turn simultaneously will be satisfying the conditions 2, 3 and 4. 2 that we have just now seen, 3 and 4 right before you. So, all these condition has to be satisfied and we want to find the solution. Important thing is there are two methods to find a solution. Like every equation has methods, similarly this also has a method. We are adopting two methods. One is solution by separation of the variables and the second is D'Alembert solution. The title of the lecture has this name, D'Alembert solution. We discuss these two methods first and second, one after the other. The first is we assume that u is a function of x and t and that is equal to a function of x and function of t. So, f is a function of x alone, t is a function of t alone, that I have given here. Fx is a function of x alone and t of t is a function of t alone, is a must, is a mandatory. We substitute 5 in 1, the equation 1 that we have seen and the equation 5 that we have just now read, the initial conditions. This gives us a relation something like this, as you can see. 1 upon c square t d2t dt square, t is a constant, capital T, small t is a time. 1 upon capital F is a function of x alone, defined above, and it is d2f upon dx square forms this equation called as 6. You notice and keep in mind the equation 6. The left hand side of this equation 6, left hand side of the equation 6 means, I remind you again, we go like this. 1 upon c square t d2 t upon dt square, I am talking about this. And so, what now we will have after the equation 6, we will have this. The left hand side of 6 is a function of t alone, and the right hand side is a function of x only, which is very vivid here. These two cannot be equal unless each is a constant, obviously. They cannot be equal unless each is equal to a constant. So, what we write is, the left hand side that we have is 1 upon c square t d2 t upon dt square, capital T being the constant and small t is the time, should be equal to 1 upon f. 1 upon f means capital F is a function of x alone, d2f upon dx square, x is a variable, as you can see on the very first part of this lecture, all are equal to 0. Now, if this is equal to 0, what we do is that we suppose either it could be a lambda square or it could be minus lambda square. And in doing so, we have seen here the three major possibilities, as you can say. I classified very simply, because this is a very important part of this equation. What we have is d2f upon dx square is equal to 0 and d2t upon d square is equal to 0. Then we have d2f upon dx square minus lambda square f is equal to 0. And the other is d2t upon dt square minus lambda square c square capital T is equal to 0. And the third, the c possibility, is written like this. Almost it looks the same. Once I have used lambda square positive, second time I have used lambda square with a negative sign. Then the solution in these three cases are, just I told you, I avoid major calculations. The paucity of the time compels me to do so. But this is comprehensible, easy. We are not leaving anything which is a complicated mathematics. So, the solutions are in three cases. The first case is f is equal to ax plus b, a and b are constant. Second is written as like this, and the third is purely a trigonometric function, f and capital T, written as with a, b, c, d constants, cos and sine are trigonometrical ratios. We apply boundary conditions, ux comma z is equal to 0, and the second is ul comma 0 is equal to 0, all these conditions. We get here u0t is equal to f0t of t is equal to 0, and similarly equation 8. These two are obtained by boundary conditions. If you look at equation 7, easily it can be said that whether it is t of t is equal to 0 or f0 is equal to 0. Since ft or t of t is equal to 0, from 8 you can very easily write that fl also will be 0, because you can see from equation 8. We go further. Some easy calculations are done, and we obtain the solution of the given equation 1 in this particular form. U is a function of x and t, and that is expressed as a summation. Summing goes from n is equal to 1 to infinity. The first constant is Cn. The second constant is dn. That is equation 9. With cos and sine, trigonometrical ratios are befitted in this definition. And it should be mentioned that this is true for all the values Cn and dn. And then with this Cn and dn appearing in equation 9 are given by, because we have to define those two constants Cn and dn. Cn is given by this integral. Cn is equal to 2 upon L. Integration ranges from 0 to L. Fx sine of n pi x upon L dx, equation 10. And similarly, almost same is equation 11. Prior we begin this method, we need to borrow something from method 1. Method 1 means separation of variables. We proceed as follows. This equation 9 of which we were talking just now, satisfies condition 3 and 4. And therefore, equation 12 can be written very easy to look at. If you calculate with your pencil and paper, you will arrive at equation 12 and equation 13 as well. Simply put those values and we arrive at these results. What happens then is this one. If we assume that the initial velocity given by that equation 4 is 0, initial velocity is 0, then we mean gx is equal to 0, which we had in equation 13, and therefore dn is equal to 0, purely constant. If you put dn is equal to 0 and gx is equal to 0 with all these assumptions, with all these calculations, then the equation 9 obviously and readily will reduce to this relation. You notice a very important thing, that is the second step. Half sigma ranges from 1 is equal to infinity Cn sine of n pi upon L multiplied by x minus Ct, and look at equation 14, plus 1 upon 2n is equal to 1 Cn sine of n pi x plus Ct. What I want to emphasize is this term. In previous, that means in previous first term and in the second term, 14 has two parts, this one. One is half summation n is equal to 1 to infinity Cn sine of n pi upon L x minus Ct, and then. So 14 has two parts, the first part and the second part, both having this summation. Cn is a constant and sine n pi upon L, this time the coefficient is x plus Ct, previously it was x minus Ct. Now the two series in 14 I am making explicitly an accountability of these two things, which I was giving you an indication. One is summation n is equal to infinity Cn sine of n pi upon L x minus Ct, and the second is n is equal to 1 to infinity Cn sine of n pi upon L x plus Ct. These two things are obtained by putting x minus Ct and x plus Ct, the substitution, for x in 12 and for fx. The series which you are seeing here as equation 14, having these two classifications, have been named as Fourier sine series. If you are studying the Fourier integral, the Fourier analysis, you must be familiar with this name Fourier sine series. Similarly, we have a name Fourier cosine series, where instead of sine we will have cos. So we consider now, in 14 we have explained that one time in the first part of it we have x minus Ct as a coefficient, in the second part we have x plus Ct as the coefficient, and we termed it as Fourier sine series. In equation 15, look at, we consider these two added together, half is outside already, and we make it to call as a function of x and t, and so we have as the solution of the equation 1, this 15. 15 is called as the solution of the equation 1, with x minus Ct forming a function, x plus Ct is forming a function, same thing, only the coefficient differs, and we call it Fourier sine series. Here f1 is the odd periodic extension of f with respect to pi L, f1 appearing in both sides. These are all periodic functions in elementary Fourier analysis. So this is a solution 1, but we must define f1, and that is what we call f1 is an odd periodic extension of the function f with a period given by pi L. The D'Alembert solution of 1 with which we have started in the form 15 just now read can be obtained by changing the independent variables. We, like any other simple transformation, like any other simple, what do we call, substitution in integral calculus or anything, So, for example, we put x is equal to tan square theta, we say x is transformed into another variable theta, or we say e to the power x is equal to z, we say that x is transformed into z, alike, almost the same thing. We here suppose that v is equal to x plus ct and w is equal to x minus ct. We are continuing right from the beginning of equation 14. Then we had equation 15 where uxt is a function under the sigma notation. Then what we do is from 16 we differentiate and we get dv partial x, we get 1 because t is a constant 0. Then we have dw, dx is also 1 because x ct minus ct is a constant, so it converts to 0. And therefore, this relation is obtained, is a very well known relation. Do you recognize it? This relation is so important in the case of partial differentiation. This is what we call as a chain rule of partial differentiation. I have named it in the next part or in the next page from here. Du dx is equal to du dv dv dx. I go to 16 to make this understand, though I have given it here also. V is a function of x and t. W is a function of x and t, and so you can write this chain relation. There are 4 chain relations to remind you, but I do not intend to repeat the whole 4 relations here, but we go like this, is equal to du dv du dw. We differentiate the whole thing again, second order, so we get d2u upon dx square is equal to d dx of du dx, and we write it like this. And we arrive at equation 18. If you recall, in partial differentiation, this equation 18 right hand side is very familiar to us. I will remind you where we have studied. We have studied this kind of an equation in a section. We call it homogeneous functions, where we use Euler's theory or Euler's theorem. Such elegant expression like the one we have on the right hand side of 18 appear. Now, the 16 also give dv dt is equal to c and dw dt is equal to minus c. Both are constant, one is positive, another is negative. And therefore, now putting these all values, equation 19 appears. That equation 18 summarizes everything, and you get the second derivative of u with respect to t written as this particular relation. From 18 and 19 we get this, we integrate and we get du dv. This is d2u dv dw, so naturally we are integrating with respect to w, and so phi v is obtained. Phi v is what we call as a function of v. Integrate again with respect to v this time, we get u is equal to this theta v, and hence you get a solution like 20. You look at this equation 20. This equation 20 is a very important equation. However, this is called as D'Alembert solution of the wave equation, but nonetheless this equation reads in language as this: u is a function of x and t, x is a variable, t is a time. We have started, if you recall, x plus ct and x minus ct. There we had f1 and f2 written, or there we have written f1 only, these similar functions, and in place of all these, after solution, integrating and using the chain rule of differentiation or partial differentiation, we explicitly obtain 2 functions. One is theta x plus ct, that means function of x plus ct. Another is a function x minus ct. We have simply denoted by something. You can use any other thing for theta and psi, but we have said it theta x plus ct and psi x minus ct. This is what we are going to call D'Alembert solution of the wave equation. This wave equation plays a very vital role in solving all the fluid dynamical problem, aerodynamical problem, aerostatical problem, the flight of an aeroplane in a simple nature, the rockets, or viscous and non-viscous flow of liquid or a material within them, find the viscous nature. So, in other words, everywhere this D'Alembert solution plays a very, very important role. Well, viewers, we concluded, as I have told you, this unit, the first part of it. We have studied one-dimensional wave equation and the D'Alembert solution of an equation, of the wave equation. This lecture involves so many interesting things. The two very important things that we have included, one is a boundary value problem and is the initial value problem. Both are very essential in solving a differential equation, a partial differential equation. We have seen what is a wave equation, we have seen what is a one-dimensional wave equation, and we have seen how those partial simple derivatives associate to give a meaning to the application of the partial differential equations. Well, D'Alembert solution and the separation of variable are only the tools, but the basic is the one which we have studied. And having defined the boundary value problem, the one-dimensional wave equation problem that we have dealt with, you must have realized it is a very, very important thing. It applies to, as I have told you just now, to various physical problems like what we have in fluid mechanics or in magnetohydrodynamics as well. And so, all mathematical notions and meaning of all these terminologies should be made very clear in our mind, in our thinking, and in our process of solving any problem. The methods have been explained, and I believe that these solutions will make you enough authentic to solve any major problem in one dimensional using the D'Alembert solution and the methods that we have explained in these lines and in the present lecture. What we do next is another very, very important thing. We will be shifting again. Differential equations are over, but still we continue at the backdrop of it with differential equations, but we will be doing a very important name. How about disclosing that name when we meet next time? Thank you. Thank you for your attention.